Let's do a graphical solution to a linear programming problem. The motivating case is an automotive assembly plant, and this is partly motivated by a couple of different student projects I've had at different automotive assembly plants. Okay, if you ever have a chance to visit one, please do it. They're really fascinating places to see. Okay. There's three major operations in an assembly plant. There's a body shop, which puts together the chassis from rolled steel. That chassis then gets painted in the paint shop. And in final assembly, thousands and thousands of components are attached to the chassis, to the vehicle. Okay. So here's just some pictures of those three operations. And there you go. Here is an example of a body shop in the GM Grand Rapids plant, and they're making floor pans. That's the bottom of the chassis, which kind of holds everything together. A very critical component for both crash worthiness and things like noise, vibration, harshness, and ride and handling. And if you look at this, it's a huge capital investment, right? This is an extremely expensive piece of machinery. And another thing you'll notice is that nobody's there, okay? Except for this one fellow, right? So very, very few people in the body shop. It's all robotics. And then after they stamp out the parts, they send it to the robotic welders. And you can see the welders here putting together the metal panels for, looks like some Dodge or Ram trucks, okay? And again, you don't see any people working there. It's all robotic. And here's Tesla's body shop, and they have the same kind of system with robotic welders. The biggest difference is that these are aluminum chassis. They're not made out of steel, but aluminum, and aluminum is much harder to work with. And here's the paint shop, and again, the paint shop is all robotic sprayers, right? So these robots have spray heads, and they go around and coat all the different pieces of the chassis. And this is from Cadillac Assembly Plant in Shanghai. All right. Here's an example of the chassis being married to a subframe. This is an old image of here's an old Camaro, and look at those old tires they have. But down at the bottom is a subframe. You have a rear subframe that holds the back suspension and tires, and differential, and a front subframe that holds the engine, transmission, and of course the front suspension. And then the painted chassis comes down, and then they get bolted together. The same thing happens in the Tesla plant, right? But now the chassis comes down on what's sometimes called a skateboard, which has the battery pack and the electric motors and the suspension all put together in one piece. This is the final assembly, a very old picture, obviously, of a Cork, Ireland assembly plant, a Ford plant in Cork, Ireland. And you can see the different workers putting on different components. This gentleman's putting on a windshield wiper. This guy down here is putting on a wheel. And the same kind of thing happens today in assembly plants, that after the chassis gets married to the subframes, then the workers swarm along the cars as they go down the assembly line, adding different components at each workstation. Okay. So this is the problem we'll be looking at for a graphical solution. And it's very hypothetical, very simplified kind of problem. To graphic, we need two decision variables. If I had three decision variables or more, I could not graph it. So obviously this is very simple. We're imagining that there's two different types of vehicles being assembled. One is a compact car, the other is a compact SUV. They're on the same platform, so they can be made in the same assembly plant. And so we have two different decision variables, the number of cars to make per day and the number of SUVs to make per day. We have an objective function which is the daily operating profit. And these are all in terms of thousands of dollars. And so my objective function Z, right, which is my operating profit, is 1,000 times X plus 1.3 or 1,300 times Y. So every compact car contributes $1,000 to the operating profit, and every SUV contributes $1,300. Okay, so just looking at that, obviously we'd like to maximize this objective function. Like, more money is always better than less money, so we'd like to maximize that. And you just say, well, just make as many SUVs as possible because SUVs have a higher margin. But we have constraints also. So we have the 3 different operations for the body shop, paint shop, and the final assembly. And we have constraints here that we only have 3,200 hours, 3,200 hours in the body shop, right? And what I mean by hours is each of those welders take a certain amount of time, and each of those stamping operations take a certain amount of time. And if you add that all up, you end up with 3,200 hours. And of those 3,200, each car takes 4 hours in total of stamping and welding time, and each SUV takes 7 hours of stamping and welding times. Okay, and so how much, if you make an additional car, you're consuming 4 more hours of body shop time, and each additional SUV consumes 7 more hours of body shop, and we have to stay under the 3,200 hour limit. Okay, so even though it looks like with the objective function, right, that we should probably just be making SUVs, when you look here, it says, oh, SUVs consume more body shop time. Body shop is a scarce resource, so maybe we should make all SUVs. We can add some cars to the mix. The next constraint is the paint shop. We have 5,000 hours in the paint shop, and that's the total time for all the different robotic sprayers and everything else, the ovens that dry the cars and so on. But each car consumes 10 hours, and each SUV consumes 10 hours. Right? So it takes about the same amount of time to paint the cars and the SUVs. Then it goes to final assembly, and we have 3,800 hours in this final assembly. Each car consumes 8 hours, and each SUV consumes 6 hours. Okay, so what we're going to do next is graph this, right? And again, because it's two-dimensional, we can graph it. In more realistic problems where you have 10 to 100 to 1,000 variables, obviously you cannot graph it. But sort of like the logic behind it is the same, regardless of how many variables you have in the model. And so what I'm going to do is call up a really cool website called Desmos. Okay? And it allows you to do a graphical calculator. This is a pretty cool website. I learned about it from students last year. So you take 4, so the body shop constraint is 4x plus 7 times y is less than. To get less or equal to, I just hit the less than key and then the equal key and changes it to less than or equal to, and that's 3,200. Okay. Now what happened, I'm off the page. I can rescale this. I just right click my mouse and I can drag this around. And then if you use I have a little scroll wheel on my mouse. I can just scroll, make this, you can do this too. You can zoom in and zoom out like that. Okay. Until you eventually see it. There you go. We can finally see it. Okay. That's what we're going for. And so the red boundary along the top is 4x plus 7y is equal to 3,200, right? So this is just the line described by the equality here. And the shaded area is the less than part, okay? So it's shaded downwards because it's a less than constraint, less than or equal to. And to verify that, all you need to do is put some points in. For example, if you take the point 0, 0, okay? You put 0x plus 0y, and then you ask yourself, is that less than 3,200? Yes, it is. So that's the way you shade. Shade. If you take 500 and 500 and put in the equation, you'll be bigger than 3,200. So we don't want that. So what this is representing is for the body shop, all the different combinations of cars and SUVs that we could make in one day. For example, we can make 400 cars and 200 SUVs, or we can make 200 cars and 300 SUVs. And so these are the different combinations of feasible production, right? So if the plant manager came to us and say, hey, we would like to make 500 cars and 100 SUVs, we would say, good, we can do that, no problem, boss. But if the plant manager said, hey, we would like to make 700 cars and 500 SUV, we'd say, well, that's And that's a reasonable thing to ask for, but guess what? We can't do it. We just don't have the capacity. And so that's a feasible region. What I didn't say explicitly is my X and Y have to be positive, right? We're not going to make negative cars, and we're not going to make negative SUVs. So anyway, this is the constraint for the body shop, and the next thing I'm going to add is the constraint for the paint shop. And so the paint shop is 10 times X plus 10 times Y is less than or equal to 5,000. Okay, and that gives me this blue shaded area. Okay, same thing as before. The line is 10x plus 10y is equal to 5,000, and shaded below it is all combinations of cars and SUVs that we could paint in one day. Okay, now that intersects with my constraint with the body shop, right? So I just want to look at the area where those two things overlap, because you might say, hey, you could actually paint the cars up in this particular wedge, up here, but yes, you could paint that number, but you couldn't get that number out of the body shop, right? So you can't do it in the body shop. And down here you say, well, I could make these numbers from the body shop, but then I'd say, well, I can't paint them in one day, so they just have to stack up someplace. What I'm going to do with it, you want to paint them as soon as you can. And so the intersection of these two regions is what gives me the feasible region. Okay, so let's do the last constraint is with the final assembly, and that is equal to 8 times X plus 6 times Y is less than or equal to 3,800. Okay, and that gives me the constraint for the final assembly. And again, there's the line, and then shading goes downward. And where these three areas intersect each other is the feasible region, right? You can just trace them along here. Okay. This top boundary is called the efficient frontier, right? Because regardless of what the profit function is, you'd like to, generally speaking, you'd like to make as much as you can. You'd like to use your resources as efficiently as possible. And so this front top boundary line is telling me, hey, that's the maximum I could utilize my resources. This is the most I can get out of the plant, right? This is the most I can produce given my resource base, okay? Given my resource constraints is this top line up here, and that's called the efficient frontier. Okay, so nowhere on this is the profit. If you really want to know where the profit is, it's a third dimension, a z dimension that comes out of this plane, right? So for every combination of x and y, I get a z or a operating profit function. So let me just go ahead and put an example of what was known as a z line in. I'm going to put the objective function down, 1x plus 1.3 times y, right? Every car adds $1,000. Every SUV adds $1,300 of operating profit. And I'm just going to pick a number. I'm going to set that equal to something. Let's just set it equal to 800, for example. Okay. And there's a Z line. I also call it here an ISO profit line in the sense that it's describing the combinations of X and Y that will lead to 800. And that would be $800,000 a day. Okay. And so that can't really get too precise here, but if you're doing 300 cars and maybe like 375 SUVs, you will be making $100,000. Or if you did 150 cars and 500 SUVs, you'd be making $800,000. Okay. Of course, you'd say, hey, I could do better. Maybe I can get up to $900,000, okay, which is more money. I like that even better. But of course, in both of those cases, you have an issue. And the issue is it's in the infeasible region. We can't make enough cars and SUVs to make $900,000, right? So as I change this coefficient, what happens is this line will move up and down, okay? The slope of the line stays constant, but where it's located goes up and down. So if I go back to 800, you can see it there. If I go down to 700, you can see it there. Let's go down to 500. Okay, we're finally in the feasible region. Okay, so there are combinations now of cars and SUV such that I can produce them and make $500,000 a day, right? It's just all these combinations along this line. So 300 and 150, or 200 and 240, whatever it is. I can make those combinations, and they'll give me $500,000. Well, that's okay, but I like more money than less money, right? And so, hey, can I do 600? Well, yes, I can. I can make it up to 600,000, and I get everything along here. Well, can I go up to 650? Well, no, I went outside the feasible region, so 650 is too much. How about if I go down to 610? Oh, okay, I can do 610. I'm still have a region, this feasible region, right? Just along here, this little bit. But I'm not being quite as efficient as I can be. How about 620,000? Okay, that's where it just hits, right? This is where the Z line, the isoprofit line, is just tangential to the efficient frontier, or to the feasible region. And this is where the magic happens. It just kisses here at 100 and 400. Okay, so if I make 100 cars and 400 SUVs, I'll come out with a daily operating profit of $620,000 a day. And I'm using my resources as efficiently as possible. So this is where my optimal solution is. Okay, so that's how you do a graphical solution to a linear programming problem. You can do it with 2 dimensions. Once you get into more than 2 variables, it becomes more difficult. And in follow-up videos, we'll see how to put this into Solver and let Solver do the work for us. Okay, thanks so much. I hope you got something out of this video. I hope to see you in other videos. Bye for now.